Okay, in today's lecture, we'll be covering section 4.5 on the chain rule for multivariable functions. And this is going to be a generalization of the chain rule that we talked about in single variable calculus, extended now to functions of two or more variables. So before we present the most general case of this chain rule, it's a little bit complex to look at the general case right away. So let's start by looking at a couple of special cases of this multivariable chain rule. So the first case we'll consider is the chain rule in the case that we have one parameter. So the idea is the following. If we have a quantity, z, which is defined as a function of two variables, x and y, where both x and y are functions of t. So here this variable t, or parameter t, might represent time, and x and y, these two quantities, could be dependent on time. So that means then that z, which was a function of x and y, well, if x and y depend on t, then z itself is a function of t. And if I wanted to find the derivative of z with respect to this parameter t, we would do the following. So we would start by differentiating our function z with respect to its first variable. So we're looking at the partial derivative of z with respect to x. But now x is a function of t, so we would have to multiply by the derivative of that inside function x with respect to t. But now since we have a multivariable function, we would then need to also include the derivative of z with respect to y, times, since y is a function of t, the derivative of our inner function is the derivative of y with respect to t. So this is the version of the chain rule for multivariable functions if our individual variables, say x or y, are dependent on a single parameter t. So now that we've looked at this multivariable chain rule in the case that we have a single parameter, let's look at some examples. So in our first example, we have z is defined as x squared y cubed plus 2xy squared, and we are told that these variables x and y depend on t. X is defined as sine of t, and y is e to the 2t. And we are asked for the derivative of z with respect to t at a particular time, namely when t is 0. So using this multivariable chain rule, if we want to find the derivative of z with respect to t, we would first need to find the partial derivative of z with respect to the first variable x, and then multiply by the derivative of x with respect to t, and then add the partial derivative of z with respect to y times the derivative of y with respect to t. So let's see what we have here. We have dz dt is equal to, well, our partial derivative of z with respect to x is 2xy cubed plus 2 times y squared. And then we're multiplying by the derivative of x with respect to t. So here the derivative of sine of t is cosine of t. And then we are adding the partial derivative of z with respect to y, which is going to be 3x squared y squared plus 4xy. And we're multiplying on the end by the derivative of y with respect to t, which in this case is 2e to the 2t. So this would be the derivative of z with respect to t. We see it depends on t, x, and y, and we're asked for the value of this quantity when t is equal to 0. Now we just mentioned, well, okay, our derivative depends not only on t, but also x and y. So let's ask ourselves, well, if t is 0, what would the values of x and y be? So here we have equations for x and y in terms of t. In the problem statement, we were told x is sine of t. So if t is 0, we have sine of 0 or 0. And if t is 0, then y is e to the 0 or 1. So we're now going to take these expressions and substitute them into the expression that we had for our derivative. dz dt is given by 2 times xy cubed. Now if x is 0, we have 0 plus 2y squared. So here, since y is 1, we have 2 times cosine of t. So now if t is 0, we have 1. And then we are adding 3x squared y squared plus 4xy. But if x is 0, this entire term reduces to 0. And then we're multiplying by 2 times e to the 0, which leaves us with 2. So altogether, we are left with just 2. The second term is 0 since our first factor was 0, and we're left with a value of 2 here. So one application of this multivariable chain rule might be in addressing related rate problems for quantities which depend on more than one variable. So we'll look at an example of this in our next problem here. We are told that the radius of a circular cylinder is decreasing by 1.2 centimeters per second, and its height is increasing at a rate of 3 centimeters per second. And we're asked at what rate is the volume of this cylinder changing when the radius is 80 and the height is 150. So let's start by maybe visualizing what we're working with here. We've got a circular cylinder. So let's sketch our cylinder here. And we're told that we're interested in its volume and how the volume is changing based off changes in the radius of our cylinder, which I will call r, and its height, which I'm going to call h. Now, we are told, or we're asked, about the volume, or the rate at which this volume is changing at a particular moment. So let's recall how to find the volume of a circular cylinder. Well, we would take the area of the base, so area of a circle, which is pi r squared, and then multiply by h, the height of our cylinder. So if we're interested in finding the rate at which the volume is changing, we need to find the derivative of volume with respect to time. Now here, our expression for volume depends on two variables, r and h. We can think about our volume as being a function of two variables, r and h. So if we want the derivative of v with respect to t, we would need to make use of this multivariable chain rule with a single parameter. So this chain rule says, in order to find our desired derivative, we would first take the partial derivative of v with respect to our first variable, r, and then multiply by the derivative of r with respect to t, and add the partial derivative of v with respect to the second variable, h, times the derivative of h with respect to t. So let's look at what we have here. We find dv dt is given by, well, the partial derivative of v with respect to r would be 2 pi r h. And then we're multiplying by the derivative of r with respect to t. And then we would add the partial derivative of v with respect to h, which gives us pi r squared, times the derivative of h with respect to t. So now let's see what we have for these quantities. We were told in the problem statement that we're interested in the moment when our radius is 80 and the height is 150 centimeters. So let's plug in those quantities for R and H. R is going to be 80, H is 150. So looking back at our derivative, we have dv dt is equal to 2 pi times R, which is 80, times H, which is 150, and then we're multiplying by the derivative of R with respect to t. Now, the derivative of R with respect to t is a measure of the rate of change of our radius. And we were told in the problem that the radius of our cylinder was decreasing at a rate of 1.2 centimeters per second. So our derivative of R with respect to t is negative 1.2. Now the negative comes from the fact that the radius is decreasing. It's a negative rate of change. And our derivative of height with respect to t, well, we were told that the height is increasing at a rate of 3 centimeters per second, so dh dt is going to be positive 3, a positive value since it's increasing. So let's substitute these other expressions into our expression for dv dt. So here we would have a negative 1.2 for the derivative of r with respect to t. And then we are adding pi times r squared. Here r was 80, so 80 squared, times the derivative of h with respect to t, which was 3. So if we simplify these terms, we are left with altogether a negative 9600 pi. And since we were measuring all of our lengths in centimeters, this unit for volume, or the rate of change of volume, would be cubic centimeters per unit time. Well, everything with our rates of change were measured in terms of seconds, so per second. So here, with the information we're given in the problem about the radius and the height and the rates at which these quantities are changing, we find that the volume of our cylinder is decreasing at a rate of 9600 pi cubic centimeters per second. So one nice application of this multivariable chain rule is involving related rate problems, which now involve multivariable functions. So in the next part of our lecture, we will consider a slightly more complicated case of the multivariable chain rule, the case where our variables depend on two parameters. So in this case, the setup is pretty similar to what we were looking at earlier. Let's suppose that we have a function of two variables, x and y, where each of these variables, x and y, are functions of two parameters, s and t. So x and y are now both multivariable functions of these two parameters, s and t. So if z depends on x and y depend on s and t, that means that z is a function of s and t. And so we could talk about finding the partial derivatives of this function. So let's start by defining how we would find the partial derivative of z with respect to s. So it would work pretty similar to what we saw in the last case with a single parameter. If I want the derivative of z with respect to s, I would first take the derivative of z with respect to its first variable, x, and then multiply by the derivative of x with respect to s. And then I would add the derivative of z with respect to y times the derivative of y with respect to the second parameter s, or first parameter s. Now, if we were interested in finding the partial derivative of z with respect to t, we would first differentiate z with respect to x, and then multiply by the partial derivative of x with respect to that parameter t, and then add the partial derivative of z with respect to y times the partial derivative of y with respect to that parameter t. So it works sort of similar to what we saw in the case of a single parameter. We could just define two partial derivatives of z with respect to either parameter now, with respect to s or with respect to t. So let's look at an example of this. In our first problem, we are told that if z is defined as e to the x cosine y, and x and y are defined as st squared or s squared t, we want our partial derivatives of z with respect to s or t. So let's start by finding our first partial derivative, the partial derivative of z with respect to s, which, using this multivariable chain rule, would be given by the partial derivative of z with respect to the first variable x times the partial derivative of x with respect to s plus the partial derivative of z with respect to its second variable, y, times the partial derivative of y with respect to the parameter s. So what we have here is the following. Partial of z with respect to x is e to the x cosine of y times the partial derivative of x with respect to s, which would be 1t squared. Then we add the partial derivative of z with respect to y, which is negative e to the x sine y, times the derivative of y with respect to s, which would be 2st. So we have the following expression for the partial derivative of z with respect to s. Now let's do the same sort of thing to find our partial derivative of z with respect to the parameter t. So again, using this chain rule, we would differentiate z with respect to its first variable, and then multiply by the partial derivative of that variable with respect to our parameter t. And then add the partial derivative of z with respect to y times the partial derivative of that parameter or that variable y with respect to our parameter t. So we find the partial of z with respect to t is given by, the partial derivative of z with respect to x is, again, e to the x cosine of y times the partial derivative of x with respect to t, which is 2st. And then we would add the partial of z with respect to y, which is, again, negative e to the x sine y, times the partial derivative of y with respect to t, which is s squared. So we arrive at the following expressions for our partial derivatives of z with respect to the parameters s or t. Now, one thing I'll mention in this example is that both of our partial derivatives that we just found depend on x, y, s, and t. Now, in some cases, we might want to express these partial derivatives only in terms of the parameters s and t, instead of leaving these things in terms of x and y. Now, if we wanted to do that, we could take this expression that we have for x, namely s times t squared, and everywhere that we had an x within our solution, we would replace it by s times t squared. Now, it gets a little messier if we do that instead of just leaving it in terms of x, but for certain problems, we might be told to express our answer only in terms of s and t. Now, similarly, we have y is defined as s squared times t, So in our solution, anywhere that we have a y, we might replace that y by this s squared times t. So here it's just sort of a matter of personal preference, but I think there might be one or two web work problems where the instructions state to express your answer only in terms of s and t. So you would need to plug these expressions that you found into your answers below. Okay, so let's look at another one, very similar to what we were just considering. In this next problem, we have z, which is a function of two variables, x and y, and x and y, which are functions of two parameters, s and t. And again, we want our partial derivatives of z with respect to s or t at a particular point, namely when s and t are equal to 2 and 0. Now, before we proceed with finding these partial derivatives, we saw in our previous example, in all of the examples so far, that when we take our partial derivatives with respect to a parameter, usually we don't get something that only depends on s and t. It usually depends on, say, x, y, s, and t. So we might start here by finding the values of x and y that correspond to the given point st. So here, if s and t are defined as 2 and 0, then let's think about what x and y are defined as. So here, x is s times e to the t power, which would give us 2 times e to the 0, or just 2. And y is s times e to the negative t, which is also 2, in the case that s and t are 2 and 0. So now that we have the values of x and y at this point of interest, let's proceed with finding our partial derivatives. So here, the partial derivative of z with respect to the parameter s is given by the partial derivative of z with respect to x, which is 2x minus 6xy cubed, times the partial derivative of x with respect to s, which would be e to the t. And then we add the partial derivative of z with respect to its second variable, y, which is negative 9x squared y squared, times the partial derivative of y with respect to s, which is e to the negative t. So at our point 2, 0, let's see what we have. So at the value, or at the point st equals 2, 0, we have our partial derivative of z with respect to s is equal to, let's see what we're left with. This 2 times x minus 6xy cubed gives us a negative 92 times e to the t. Now if e is 0, or excuse me, if t is 0, we have e to the 0 or 1, and then we are adding negative 9x squared y squared. So if both x and y are 2, we have negative 9 times 16, or negative 134, times e to the t, and if t is 0, we have a 1. So simplifying here, we're left with a negative 226. And for our other partial derivative, that is the partial derivative of z with respect to t, we would first differentiate z with respect to the variable x. So again, we have 2x minus 6xy cubed times the partial derivative of x with respect to t, which would be s times e to the t. And then we add the partial derivative of z with respect to y, which is again negative 9x squared y squared, times the partial derivative of y with respect to t, which is negative s times e to the negative t. So again, at our point of interest, st equals 2, 0, where we found x and y are equal to 2, 2. We have the partial derivative of z with respect to t is equal to negative 92 times 2 minus our 134, same as what we had before, times negative 2, which reduces to a positive 84. So this would be the value of our partial derivatives of z with respect to the parameters s or t at the indicated point. All right. So now that we've considered a couple of examples of this chain rule for multiple variables in the case of just one or two parameters, let's state the more general or most general version of the multivariable chain rule. So here's what it says. Let's suppose that we have a quantity u, which is a function of n variables, x1, x2, up through xn, and each one of these variables, x1, x2, up through xn, is itself a function of m parameters, t1 through tm. So that means that my quantity u is a function of t1 up through tm, each of these parameters. And if I wanted to find the partial derivative of my function u with respect to one of those parameters, say the ith one, t sub I could start by differentiating u with respect to its first variable x1, and then multiply by the partial derivative of that variable, x1, with respect to whatever parameter I'm interested in this case, t sub I. Then we would add the product of the partial derivative of u with respect to its second variable, x2, times the partial derivative of x2 with respect to the parameter t sub I. And we would keep adding these products of partial derivatives until we get to our last variable, the derivative of u with respect to x sub n times the derivative of that variable x sub n with respect to my parameter of interest, ti. So in general, we can define this chain rule for a function of any number of variables where each of those variables could be a function of any number of parameters. So to illustrate this more complex case, let's consider the following example. We have a function u, which depends on x, y, and z, so a function of three variables, and we are told that x, y, and z are defined as functions of three parameters, r, s, and t. And we are asked to find, in this problem, the partial derivatives of our function u with respect to each parameter, r, s, or t, at a particular point, namely when r is 2, s is 1, and t is 0. So here, let's start by finding our partial derivatives of this function u with respect to each parameter. So starting with the first parameter, partial of u with respect to r, well, using the multivariable chain rule, we would first differentiate u with respect to its first variable x, and then multiply by the partial derivative of x with respect to our parameter of interest r. Then we add the partial derivative of u with respect to y times partial of y with respect to r, and then the sum of partial of u with respect to its last variable z times the partial of z with respect to r. So let's see what we find here. The partial derivative of u with respect to r is equal to. So for this first term, the partial derivative of u with respect to x, we have 4x cubed y. times the partial of x with respect to r, which gives us s times e to the t. And then we add the partial derivative of u with respect to y, which is x to the fourth plus 2yz cubed, times the partial derivative of y with respect to r, which is s squared times e to the negative t. And then our last term, we have the partial derivative of u with respect to z, which is 3y squared z squared, times the derivative of z with respect to r, which gives us a 2rs times sine of t. All right. Now, for our next partial derivative, that is the partial of u with respect to the second parameter s, we would approach it in the same way. We have the partial derivative of u with respect to the first variable, and then multiply by the partial derivative of x with respect to the parameter s, plus the partial derivative of u with respect to y, times the derivative of y with respect to s, plus the partial of u with respect to z, times the partial of z with respect to s. So here we have the partial derivative of u with respect to s is equal to, again, 4x cubed y, now multiplied by the partial derivative of x with respect to s, which gives us an r times e to the t, plus the partial of u with respect to y, which is, again, x to the fourth plus 2yz cubed, times the partial derivative of y with respect to s, which is 2rs e to the negative t, and then plus the partial of u with respect to z, which is, again, 3y squared z squared, times the partial derivative of z with respect to s, which gives us r squared times sine of t. And now for our last partial derivative, that is the partial derivative of u with respect to t, we would approach in the same way. So again, we start by looking at the partial derivative of u with respect to its first variable, x, times the partial of x with respect to t, plus the partial of u with respect to y, times the partial of y with respect to t, and then plus the partial of u with respect to z, times the partial of z with respect to t. So what we're left with is the following. As with our earlier partial derivatives, partial of u with respect to x is 4x cubed times y, times the partial derivative of x with respect to t is r times s e to the t, plus the partial derivative of u with respect to y, which is, again, x to the fourth plus 2yz cubed, all times the derivative of y with respect to t is negative rs squared e to the negative t, and then plus the partial derivative of u with respect to z is, again, 3y squared z squared, times the partial derivative of z with respect to t, which gives us r squared times s times cosine of t. So now we have all of our partial derivatives of this function u with respect to r, s, and t, and we are asked about the value of these partial derivatives at a particular point, namely when r, s, and t are defined as 2, 1, or 0. Now, looking at the expressions that we have for these partial derivatives, we see they also depend on quantities like x, y, and z. So we need to find what are x, y, and z for these values of our parameter. So as we did in our earlier example, at the point defined by r, s, and t, are equal to 2, 1, and 0, we have the variables for our function x, y, and z are defined as, well, let's look at x. X was defined as r times s times e to the t. So we are left with 2. Y was defined as r s squared e to the negative t. So also 2 for these parameter values. And then z is r squared s times sine of t. Now if t is 0, we have sine of 0, which is 0. So we're going to take these expressions for r, s, and t, x, y, and z, and substitute them into the partial derivatives that we found above. So what we have is the partial derivative of u with respect to r is equal to 4 times x cubed times y. So notice for each of these partial derivative expressions, we have that same expression, 4x cubed times y. Now, since x and y were found to both be 2, we have 4 times 2 cubed times 2, which leaves us with 64 times. For this next term, we had s times e to the t, so here times 1, plus for the next term in each one of these partial derivatives, we had the same expression, x to the 4th plus 2y z cubed. Now z is 0, so we really just have x to the 4th. And if x is 2, we have 2 to the 4th, or 16 for each of these terms, times for the partial derivative of u with respect to r, we were multiplying by s squared times e to the negative t, which gives us a 4 if s was, or excuse me, a 1 if s was 1. Then we are adding for this last term in each of our partial derivatives, we had this 3y squared times z squared. Now z is 0. So this last term just gives us a 0. We don't care what we're multiplying by on the end. So for this partial derivative of u with respect to r, we're left with 64 plus 16, or 80. Now let's move to the partial derivative of u with respect to s. So again, we mentioned that all of these partial derivatives start with the same expression, 4x cubed times y, which we found from our earlier work as equal to 64. Now for the partial derivative of u with respect to s, we're then multiplying by r times e to the t, which gives us 2, plus, for our next term, we have a 16 times the partial derivative of y with respect to s, which was 2rs e to the negative t, which gives us 4. And then plus our last term we said is 0. That 3y squared z squared will give us 0. And here we simplified to 192. Now in our last partial derivative, the partial of u with respect to t, well, we have our 64. We are then multiplying by r times s times e to the t, which leaves us with 2. Plus, for this next term, we have, again, 16 times the partial derivative of y with respect to t, which was negative r s squared times e to the negative t. So for our parameter values, we're left with a negative 2, plus that last term, 3y squared z squared, is 0. And so this simplifies to a 96. So we find the following values for these partial derivatives. So this last example illustrating that the more variables that your function depends on, or the more parameters that each of those variables depends on, we have some more complicated expressions for these partial derivatives, but we can save ourselves a little bit of work if we recognize that some of these terms will repeat. So we don't have to calculate these numbers separately each time if we recognize the fact that these partial derivatives of u with respect to x, y, or z yield the same expressions. So we can simplify our work if we make use of that fact. So in our last example for this section, we are asked to verify that a certain relationship among the partial derivatives of a function z with respect to x, y, or parameters s and t is satisfied. And here the function that we're working with is z is equal to an arbitrary function f of x and y, where the variables x and y are functions of two parameters s and t, and we want to show that the following relationship holds. So there's a few ways we could go about doing this. I'm going to start by calculating my partial derivatives on the right-hand side with respect to my parameters s and t. So for this first expression, the partial derivative of z with respect to s, using the multivariable chain rule, we would first differentiate z with respect to the first variable x, and then multiply by the derivative of x with respect to that parameter s. And then we add the partial derivative of z with respect to the second variable y times the partial derivative of that variable with respect to our parameter s. So let's see what we get. We have the partial of z with respect to s is equal to the partial derivative of z with respect to x times the derivative of x with respect to s is just 1. And then we add the partial derivative of z with respect to y times the partial derivative of y with respect to s, which is also 1. So this simplifies to the sum of the partial derivatives of z with respect to x and with respect to y. Now on this right-hand side, we are also asked for the partial derivative of z with respect to the parameter t. So let's find that partial derivative with respect to t. Again, making use of the multivariable chain rule, we have the partial derivative of z with respect to x times the derivative of x with respect to t, plus the partial derivative of z with respect to y times the derivative of y with respect to t. So that leaves us with the derivative of z with respect to t is equal to the partial derivative of z with respect to x times the derivative of x with respect to t, which is 1, plus the partial derivative of z with respect to y times the derivative of y with respect to t, which is -1. So we can simplify a little bit. We find the partial of z with respect to t is partial of z with respect to x minus the partial of z with respect to y. Now on this right-hand side of our equation, those two expressions that we just found, we're supposed to take the product of. So let's look at the product, partial of z with respect to s times the partial of z with respect to t. So using what we've just found above, well, partial of z with respect to s is the partial of z with respect to x plus the partial of z with respect to y. And then we're multiplying by the partial derivative of z with respect to t, which is the partial of z with respect to x minus the partial of z with respect to y. So if we expand this, we find we have the partial derivative of z with respect to x, quantity squared, minus the partial derivative of z with respect to y, quantity squared. And that's exactly what we wanted to show. We wanted to show that that product is equal to the difference of these squares. So we've established our result here. So if you have questions on any of this material, it's a little bit tricky. It's certainly kind of a pain to write out notationally all these different partial derivative symbols when we work through these problems. But if you have questions on any of this, of course, always feel free to email me for some clarification or to see some more example problems worked out during